This is a video going through problems 2, 5, and 6 on the review for test 7A. So this problem right now is on page 38. 2 and 5 are on page 38, and 6 is on page 39. These are problems similar to what is on the take-home test. So Terry purchased a guitar in 2002 for $13,000. Experts estimate that its value will increase by 12% per year. Write a function to model the growth in value for this guitar. So remember, we're talking about exponential growth, exponential decay. And recall, we have a couple of options when we talked about this in class, tracking time. So we can either set it up like that, and it's 1 plus. I'm using 1 plus because we're talking growth. That's why I'm not using 1 minus. Well, I am going to use this one because we're given a percent. When you're given a percent, this is the model we're going to use. So we know that, get rid of this now. A is the value of the guitar. R is the rate that it's growing as a decimal, so 0.12, and we're ready to go. 13,000, 1 plus 0.12, so that can be written like this, 13,000, 1.12 to the t. And there's our answer. To the t power. I want to make sure you're clear on that. It's not times t, to the t. So let's make sure that I make that very clear when I'm writing this. Just a little t up there. So now the next part, okay, there it is. Let's answer part B. Predict in what year the value of the guitar will be 70,000. So now is when we use our calculator. So if I open up my calculator, I already did this ahead of time. I went to the y equals button and I typed in the model, 13,000, 1.12, and I hit the caret button, raised it to the X because there isn't a T on the calculator. And we hit graph. If yours doesn't look like this, remember we hit zoom 0. And then it will look like that. And I graph it just to make sure that does my model make sense? If my graph was going down and to the right, we'd have a problem because the guitar is growing. So my graph better go up and to the right. And it does. So now I hit second graph so I can look at my table. And all I'm doing now is I'm looking at the Y value. And when is the first time the Y value will jump above 70,000 or be right at 70,000? It's not at 70,000 though. We have 63,532. So that's not my answer. 71,156. So after 15 years, the value of the guitar will be 71,156. So let's write that down. So when x is equal to 15, y was equal to 71,156. That was the value of the guitar. So we're in the year 2002 right now. So in 15 years, we will be in the year 2017. That is the year that the value of the guitar will be $70,000, approximately. Really, the true value will be 71,156. We're making a prediction. I'm not doing partial years here. So the first time was after 15 years. After 14 years, the value wasn't above. It was at 60 something thousand. All right, let's go to problem number 5. The value of a truck bought new for $34,000 decreases 8.5% each year. Key word, decreases. So we know we're going to be dealing with decay. Also, we have a percent. All right. Assume the current year is 2014. Write a function to model the depreciation and value of this truck. So I know I'm going to use this. I have a percent and it's depreciating, decreasing. So it's 1 minus. So I know the value of the truck is $34,000. So that's my A. My R is 0.085. Remember, with a percent, you change it to a decimal. You have to move the decimal 2 places to the left, 0.085. So 1 minus 0.085. 1 minus 0.085 is 0.915. And there is our model. That represents the depreciation and value of the truck. So now we're going to predict in what year the value of the truck will fall below 6,000. Grab your calculator out, go to y equals, and obviously if I'm going too fast, and you can hit stop, that's the joy of the video, 0.915 caret x graph. I'll probably have to hit zoom fit again, or zoom 0. It's the same thing. Zoom fit, zoom 0 is the same thing. It looks good. I mean, I know it's going down and to the right, and it needs to because it's a decay. I'm going to just hit zoom 0 just to see what happens if my graph changes at all. A little bit, but the first one was just fine. It's just getting an idea. The graphing it is making sure that is your model correct? Because like I said, if my exponential function is going up and to the right, something's wrong because we're depreciating. It has to go down and to the right. Second graph. So now I'm going to scroll down because I want my y value to be below 6,000. So I keep going. There it is. After 19 years, the value is 6287.5, but after 20 years, it's 5753.1. So let's write that down. When x is equal to 20, y is 5753.1. It's the first time it falls below 6,000. So predict the year. Well, we're in the year 2014 right now. And after 20 years, we'll be in the year 2034. So I'll write this one out in words, actually. So in 20 years, the value of the truck will fall below $6,000. Example 6. Certain car depreciates about 11% per year. Write a function to model the depreciation and value for a car valued at $30,000. All right, the car is worth that. R is going to be 0.11, and I know that I'm going to use 1 minus r to the t because it's depreciating. So my model, 1 minus 0.11. And that is 0.89. Okay. There we go. The next question. Suppose the car was worth $30,000 in the year 2003. What is the first year that the value of this car will be worth less than half of that value? Well, half of 30,000 is 15,000. That's what we're going to look for. We're going to look for when the Y value is below 15,000. That's what half means, half of this value. Calculator, Y equals, clear that out, 30,000, parenthesis, 0.89, caret, X, graph. I'm good. I'm not going to hit zoom 0. This looks good. It's going down and to the right. I'm good with that. I'm going to go right to second graph because I want my table. And let's see, 15,000 is what we're looking for. All right, so we can't use X equals 5 because that's 16,000, but we can use X equals 6, 14,909. So let's write this down right now. Let's write down what we know. Okay, done a couple of things here. We have our X, we have our Y. At time 0, when we start, this is how much the car is worth. That is in the year 2003. After 6 years, now the car is worth 14,909. Well, that would be obviously in the year 2009. It's kind of writing this out. So that's really our answer, 2009, because we started in 2003. After 6 years, the value of the car will be worth 14,909. So that's less than half of the 30,000. Done. All right. So I did those problems I promised I would do on the review. I want to quickly now open up the take-home test. Let's read through this. It says use graphing technology, obviously. A certain type of car depreciates about 15% per year. The value of the car in 2015 was 20,000. Write a function to model the depreciation in value for a car valued at 20,000. I just did a couple problems just like that. What was the value of the car in 2020? We'd use our calculator. If we're starting in 2015, 5 years later, we're at 2020. So we need to look at the calculator and use the Y value after 5 years. What is the first year, now we're solving for X time, that the value of this car will be worth less than half of that value? When they say half of that value, they're referring to the value of the car in 2020. So you have to answer part B first, take half of it, and then you can solve it similar to how I did on the review problems I just did. Number 2, for a certain bacteria, the cells double. We did a problem like this in class when I taught the lesson. If something's doubling, it's obviously growing. Suppose you cut your hand and 10 bacteria cells get in the cut. For all of the questions, assume that there's no treatment for the cut or infection. So we're going to write a function to model the growth. Since there is no percent on this one, I don't think it's going to let me write on here, and it's not. But there's no percent on this one. So you want to make sure on that one, on number 2, I'm just going to a new screen here. You want to make sure that you're using that model. And I want to go back a minute and check something. All right, we're modeling. Model the growth of the number of bacteria. Growth of the number of bacteria cells. Okay, yeah, per hour. That's what I wanted to look at. All right. So that's what we're going to use. Based on this, we can tell that A is 10 and B is obviously going to be 2. Double goes with 2. So you're writing a function. Now, suppose you waited for 8 hours to get your cut treated. Oh, 8. That's our time. How many bacteria cells would there be in your cut? You're using the model you created in A. You can use a calculator there. This one, you could do it by hand if you wanted to. You could just plug it into the model. And then you're going to definitely want to use the second graph button to get the table. How long would it take for there to be 1.3 million 1310720 bacteria? How long? Now you're obviously solving for your X or your T time, and you would use the table feature of the calculator. Please let me know if you have questions.